Hi everybody. Today we're going to continue our discussion on electric circuits, and as we learned last time, the three basic parts of a circuit being the current, the rate of flow of charge, the resistance, whatever tries to slow down that flow of charge, and voltage, the thing that is actually pushing the charge through a circuit. Today we're going to look at how all three are actually related, and it's going to be related in two different ways, something called Ohm's Law and something called Joule's Law. Kind of relate all these things together. So to begin with, the idea of Ohm's law, okay, is a way of linking those three things, voltage, current, and resistance together. Now, interesting enough, Ohm's law is not a true law of nature like, for example, Newton's second law of motion, F equals ma. It's an experimental law that works, 99% of the time, but because it's not 100% of the time, it's not a true natural law. There are some flaws in it, but it works enough times that I guess it was given sort of law status. But in the end, it's really just an equation. It says that voltage is equal to current times resistance. V equals IR. V equals IR. Okay, pretty convenient, easy way to look at it. Although it's really not the best way to actually write that equation. Because if you think about it, current is the rate of flow of charge. And it turns out that your current can be changed if you alter what you're pushing with or if you alter what your resistance is. Now remember, to change resistance, we have to change things like material, area, length, things like that. To change voltage, well, we have to be able to increase or decrease that. So current seems to be the one that is actually truly affected. So one of the best ways to really consider Ohm's law is to rewrite it like this. I equals V over R. Because in the end, it's current that gets affected. And if we look at this, current must be directly proportional to resistance. So if I increase the push, then I will get more current flow go through there. So, for example, if I double my voltage, I should double my current. But current and resistance appear to be inversely proportional, which means as my resistance goes up, my current will go down. So that if I were to double the resistance, I would get 1/2 the current. Well, let's look at a simulation and see how this all works. Okay, so what we have here is what we kind of call a simple circuit. We have a single voltage source here, a 12-volt battery. We have a single resistance here. Now, basically, we're going to ignore an existence in the wires. So the resistance of the wire has been set to 0. We're going to focus solely on just this light bulb as a resistor. So it has a 6 ohms of resistance. Now, one thing you'll notice is right now it's saying that there is no current. In fact, we don't even see the charges represented in blue here moving at all. Well, that's because there's a switch here. And it turns out that in order to have current flow, you have to have what's called a complete path. In other words, there has to be a way for the charge to get from the high of the battery, the high potential, to the low. So that if I break that circuit anywhere, the current can't flow. So that when we close the switch, now we've completed the circuit. By the way, you'll notice it's actually showing true current because this is supposed to be the negative and this is the positive, and it's actually going negative to positive. Now, kind of what's really happening here is, again, the battery is the source of voltage, the thing that's pushing the charge. Okay, so it actually kind of pushes these electrons along, and because they repel each other, they naturally move the one next to each other. So they continually go around here, giving this light bulb some electricity. Now, if Ohm's law says that current, which you'll see is 2 amps, okay? 12 volts, 6 ohms, 2 amps. Well, 6 times 2 is 12. That seems to work. Well, let's say I double my voltage. Now, one of the ways to double my voltage, well, let's add another battery. One right after the other. Now I have two 12-volt batteries, giving a total of 24 volts of potential difference. Okay? And since I didn't change my resistance, when I double the voltage, that actually doubled the amount of current. So again, showing that voltage and current are directly proportional. It's basically saying that I have a much more powerful push. So even though I haven't changed the resistance, I'm pushing harder, and that allows it to go much faster. All right, so okay, let's go back to our original premise where we had a 12-volt battery, 6 ohms resistance, and that gave us 2 amps of current. Now let's double our resistance. Now notice, as soon as I doubled my resistance, made it harder for the charge to flow, the current cut in half. Again, showing the fact that current is inversely proportional to the resistance. So as you can see, voltage doesn't depend on current. Voltage is set by whatever is created here. Resistance doesn't depend on current. Resistance is set up by materials, length, area, things like that. But current is the thing that is always affected. Current is affected by voltage. Current is affected by resistance. Keep that in mind. So let's look at a couple of examples here. I've got 3 different light bulbs where I know different things. In my first one, I know I have a light bulb that requires 0.2 amps to run when plugged into a 120 volt socket. And I want to know what the resistance of that bulb would be. Well, Ohm's law allows me to find that because I have 120 volts and 0.2 amps, meaning that bulb has a resistance of 600 ohms. I don't draw my ohm symbol very well. And really, it's as simple as that. In the next one, I have a 120 volt light bulb. Let's say it has a resistance of 80 ohms. And I want to know how much current that would require. Well, again, Ohm's law, 120 volts, 80 ohms, means that there would be 1.5 amps of current running through that particular light bulb. Again, not too bad, right? But let's look at this last one. Here I've got a 300 ohm light bulb plugged in 120 volts. And what I want to know is how much charge flows through this bulb every 5 microseconds. Now this involves an extra step. See, if I look at Ohm's law, the thing that's missing is I, current. So I have 120 volts and 300 ohms. That gives me a current of 0.4 amps. But now if we remember back from our previous lesson, current is defined as the rate of flow of charge, Q divided by time, charge divided by time. So I have 0.4 amps. I don't know how much charge that is, but I have 5 microseconds. Micro is 10 to the minus 6. And that tells me that there would be 2 times 10 to the minus 6 coulombs of charge passing through that light bulb every second. And that's basically it. Sort of how we can combine a lot of different things there. So that's how Ohm's law basically works. V equals IR. Now, the other relationship here that's important is something called Jules Law. Now, joules, of course, remember the idea of energy being measured in joules. This is going to relate electrical power and energy through these parts of the circuit, voltage, current, and resistance. Now again, it's just a simple equation. Power equals current times voltage. Electrical power. Okay, we're talking about electrical power here. Power equals current times voltage. Okay, pretty simple, right? Power is still measured in watts, like anything else. But there's also something interesting we can do here, a little algebra. I know everybody loves some algebra. If power is current times voltage, and we know that Ohm's law says V equals IR, well, that means power, well, wherever the V is, I can put in IR, right? So I have I times R, which gives me a second equation for power, which would be I times I, which is I squared R. Of course, we also know that current is voltage over resistance. So that means wherever an I is, I can put V over R. So I could say P is V over R, all times V, and I get a third equation for electrical power, V squared over R. So combining Jules law and Ohm's law together gives us 3 different power equations. IV, I squared R, or V squared over R, depending on what it is we're looking for. But I want to emphasize one in particular, and that is I squared R. Whenever we deal with a situation where you're asked to determine how much power is lost through something, you have to use this equation, okay? Because power loss or energy loss, well, think about when we talked about how we're going to lose energy, okay, through something called non-conservative work. That means things like friction. And we talked about resistance being a kind of electrical friction. And resistance gets its electrical friction because it's resisting current. So whenever you lose electrical energy, and guess where it mostly goes? Heat. It's the result of current flowing through resistance. Okay, that's where the heat is created. So again, one of the best ways to reduce your amount of heat and energy loss is to keep your resistance really low. That helps reduce it a lot. So whenever we talk about power loss, that's the equation you really want to go with. Okay, so for example, say I have a 60-watt light bulb that's plugged into a 120-volt socket. I want to determine the resistance of the bulb. And I also want to know the current flow through the bulb. Now there's a neat thing about this, because we don't have to do these in order. There's a couple different ways we could do this problem. But let's take it as it is. I have a power of 60 watts and a voltage of 120 volts. And I want to find resistance. Well, on those three equations, I can use power is V squared over R. 60 watts of power, 120 volts squared over resistance. By a quick little trick, you can just flip-flop these positions. So now I have 120 squared over 60, which gives a resistance of 240 ohms for that light bulb. Now, once I have that resistance, I can get the current by using Ohm's Law with 120 volts and 240 ohms. Gives me a current of half an amp. That's one way you could have done it. Now the other way we could have approached this problem is to answer part B first. Because again, if I have a power of 60 watts and a voltage of 120 volts, well, I have another power equation that says P equals IV. And if my power is 60 and my voltage is 120, well, I still get half an amp of current. And now I can go and solve part A, back to Ohm's Law, 120 volts, half an amp of current, still gives a resistance of 240 ohms. Okay, so that's the nice thing about Ohm's Law and Jules Law. You can do a lot of different things with it. Now, because we're talking about electrical power and the fact that when we often plug things in, is designed to do some sort of work for us. So often what we use electricity for is to do mechanical work. Okay? Again, my favorite example is a blender. I don't know why. But when you plug in the blender, it turns these blades, which is actually a mechanical job of spinning those blades using the electricity. So there must be a way to convert electrical into mechanical. And it turns out it's through the root of power. So let's look at an example of this. Here I say I have a 10 amp electric crane. It's plugged into a 20 volt source. And first of all, determine the resistance of the crane. Okay. Well, I've got current and voltage. So Ohm's Law will easily give me resistance. 20 volts, 10 amps, gives me the complete wrong thing. 20 volts and 10 amps gives me a resistance of 2 ohms. That's pretty easy, right? Now, determine the power required to run the crane. Now, the crane is running on electricity, so that's electrical power. Okay, so let's say IV. We have 20 volts and 10 amps, or it's a 200 watt electrical crane. In other words, it needs 200 watts of electricity in order to do whatever it's going to do. Now, part C, here's the fun part. Determine the time it takes to lift a 100 kilogram mass to a height of 4 meters. Now, lifting things up is mechanical. Okay, mechanical. So what we're saying is that this 200 watts of electrical power is going to be converted into 200 watts of mechanical power. Okay? Now, that's assuming a perfect machine, what's called 100% efficiency. In reality, that's not really going to happen, but for now, we'll pretend it can. If we remember back from mechanics, power, mechanical power, is work over time. Now, we're lifting something. So the work we're doing is work against gravity. Or in other words, we're going to give it potential energy. So let's use mgh for work over time. Now, if we look at this, I have 200 watts now of mechanical power, lifting a 100 kilogram mass in gravity to a height of 4 meters in a certain time. Again, let's just flip-flop those positions. Little algebra trick. And our time comes out to be 20 seconds in order to do that. Okay? So we were able to take our electrical power, convert it into mechanical power, and then do some sort of mechanical work. And that's how that all comes out. Now again, if you talk about the idea of efficiency, if for example this was only a 50% efficient machine, well that means yes, you would draw in 200 watts of electrical energy, but heat and all kinds of things like that in the machine would only allow you to get 100 watts of mechanical power back out. You'd lose 50% of your power, 50% of your energy. That's where the idea of something called efficiency comes in. So again, using power as work over time allows us to do that. One last thing. Have you ever wondered how much you pay for power? An interesting exercise is to go and try to get your electrical bill. And often on your electrical bill, you'll see something like $0.24 per kilowatt hour. That's how much the power company is charging you to use electricity, to buy electricity for them. So for example, let's say that your power bill says it costs you $0.21 or 21 cents per kilowatt hour. And we want to know how much does it cost to run a 100 watt light bulb for about 12 hours. Okay? Now, there's no equation, anything like that. This is actually an exercise in dimensional analysis, which is always fun to do. So let's look at what we have here. We start off, we have $0.21 per kilowatt hour. Now, the kilowatt hour is the unit the power company came up with because they're not going to use standard physics units because that would be a watt times a second. And calculating every watt of power you use every second would be big, big numbers to do. So they use this kilowatt hour. So we're going to use non-standard units here. So first of all, for 100 watts, we need to convert that to kilowatts, which gives you 0.1 kilowatts of energy. So now I have 0.1 kilowatts over 1. Now I put it up top because I want to cancel kilowatts out of here. Remember, I want to know the money value of this thing. I have 12 hours, which also goes on top because I want to get rid of hours. So the only units left is dollars. And when I multiply that all out, it turns out it costs about 25 cents to run that one light bulb for 12 hours. Now you might be thinking, hey, that's not a big deal, 25 cents, just a quarter, I got that in my pocket. But remember, that's one light bulb running for 12 hours and one 100 watt light bulb. Now imagine you start adding up all the light bulbs and your refrigerators and computers and everything like that you may have plugged into your walls and running. That starts to really add up. It's also one of the reasons why it's best to switch from a 100 watt incandescent light bulb that burns a lot of energy to maybe a 14 watt CFL light bulb or LED light bulb that gives you an equal amount of light but at much reduced cost. Okay, so that's basically the idea of how we relate the three parts of a circuit, voltage, current, and resistance, in terms of, first of all, Ohm's Law, V equals IR, voltage equals current times resistance, and Joule's law, power equals current times voltage, or the other two equations, P equals I squared R and P equals V squared over R. We'll see you next time.